right? So why do we balance equations in the first place? Well, in order to not violate the law of conservation of mass or the law of conservation of matter, right? So the amount of stuff that you start with should equal the amount of stuff that you end with. And that's from a variety of perspectives. When we balanced our equations, we made sure that the number and types of atoms that we started with equal the number and types of atoms that we ended with. Right? We can also take that idea and apply it to the actual masses of the reactants and products involved. And we can say then that the total mass that you start with should equal the total mass that you end with. So for example, if we take a look at the reaction between silver and sulfur to make silver sulfide, right? If you measure out, what is this, 215.8 grams of the silver on the left, and we add it to 32 grams of sulfur on the reactant side, we just add these two masses together, we get the total mass of the product, right? We combine these. So there is no loss of mass, there is no gain of mass. Right? That is what the conservation of mass or the conservation of matter actually mean. Now when we balance our equation, right, we stuck in or we place these coefficients in front of the chemical formula to make sure that the total number and types of atoms that we start with equal the number and types of atoms that we end with. So we start here with 2 atoms of silver combining with 1 atom of sulfur to make silver sulfide, which has 2 silvers and 1 sulfur. Right? So we haven't lost any of those atoms. We haven't gained anything extra either. So when we stuck those coefficients in, right, we, in addition to keeping or not violating the law of conservation of matter, what it gave us was an idea of the relative number of atoms or molecules involved. Right? So what this is telling us is that 2 atoms of silver react with 1 atom of sulfur to make 1, we'll say unit, because it's not really a molecule, 1 unit, we'll call it, of the silver sulfide, right? So those coefficients give us an idea of how many of each things are reacting and how many of the products we actually make in terms of either atoms or molecules. In the lab, though, are we given or do we work with number of atoms and number of molecules? Is that feasible? Is that practical to have 1 silver or 2 silver atoms and 1 sulfur atom? Do you have the tools in the laboratory or in your backyard to work with them? No, that's impossible, right, to do. Even with really, really sophisticated instruments, it's extremely difficult to do. So how do we make that balanced equation make a little bit more sense to us in terms of the actual amounts that we are able to use? Well, we can take those coefficients now and just translate them. Instead of now meaning individual atoms or individual molecules, we can now say moles of things. So we can say, for example, now 2, if we look at this equation down here, right, we can say that 2 moles of iron, Fe, react with 3 moles of sulfur to make 1 mole of iron 3 sulfide. Right? So we get those numbers simply from the balanced equation, right? The 2 here in front of the Fe tells us that we have 2 moles of Fe. The 3 in front of the sulfur tells us that we have 3 moles of sulfur. And then remember there's a 1 there in front of the Fe2S3, right? So we make 1 mole of Fe2S3. So those coefficients give us a mole-to-mole relationship from that equation. So the way that that is useful to us is we can take those mole-to-mole relationships and express them in a way that we've seen before, which is as conversion factors. Okay? Once you have a balanced equation, these conversion factors come directly from that balanced equation, right? So you have to make sure your equation is balanced. I guarantee you, if your equation is not balanced, you will end up 100% of the time with the wrong answer. So from this balanced equation, we can come up with several conversion factors. Let's take a look at a couple of them. So the first one we can do is to relate each of these reactants to each other. So we can say, for example, 2 moles of Fe for every 3 moles of sulfur. Right? I just take the coefficient of one thing and put it over the other. What do you think the other conversion factor from this would be? Just flip it like you would any other conversion factor, right? So 3 moles of sulfur reacts with 2 moles of Fe. Right? We can, as long as this is in the form of a conversion factor, we can do everything we've done before with any other conversion factor we've ever encountered. The only difference now is where we're getting that conversion factor from. And it comes from our balanced equation. Right? So you need to make sure that it is balanced before you can come up with the conversion factors. All right, let's take a look at a couple other ones. So we can also relate, in addition to the iron and sulfur, we can relate the iron to the product, the iron sulfide. Right? So we can say that 2 moles of iron produce 1 mole of the Fe2S3. Right? I put the coefficients on top of each other. 2 moles of iron for every 1 mole of the Fe2S3, and then I can flip that to get the other one. So 1 mole of the iron sulfide for every 2 moles of iron. Is there any other, are there 2 other things that I can relate in this equation? So we've related the iron to the iron sulfide. We have related the iron to the sulfur. Right, so we have one more combination. We can relate the sulfur to the iron sulfide.
So it's 2 different conversions because it's 2 different groups?
Correct. We're just we're relating 2 components, right? Either the reactants to each other or a reactant to a product. And that ratio is going to be different depending on what the coefficients are. Right? That's all we're doing here is putting in the coefficients and the word mole right after it. So our ratio here then would be, our conversion factor would be 3 moles of sulfur for every 1 mole of the Fe2S3. Or we just flip it to get the other one. Does that make sense? It's not going to work if you don't have your balanced equation, right? And once you have your coefficients in, we're just taking those coefficients and using them as a ratio of one thing to the other thing. And we flip it to get the other relationship. Don't just put your numbers in. You also want to put in, just like with the other conversion factors we've seen before, put in the entire unit, all right? Moles of what to moles of what, because that's going to help you when we start using these in calculations down the road. All right, let's take a look at another equation. So here we have hydrogen reacting with nitrogen to make NH3, which is ammonia. So before we get to the question, what type of a reaction is this?
Combination.
You're supposed to raise your hand first, and then.
She was so excited because she knew.
So it's a combination. Okay, why is it a combination reaction?
Because you're taking two separate molecules, elements,
Things.
and making one.
Right. So you're combining multiple things to make one type of a product, right? That's the opposite of a decomposition, which was one of the first clicker questions. All right. So combination reaction. Is the equation balanced? Okay, you should always ask yourself that question before you do anything to an equation. Is it balanced? Yes or no?
Yes.
No. Yes. Okay, it says yes, it's balanced. No, it's not balanced.
Yeah.
So no, it's not because there's 6 H's on that side. Wait, no, it is
There's
balanced.
six balanced.
It is
It's
balanced.
balanced.
Two nitrogens and then 6 is hydrogen. So it's balanced.
It's balanced.
So that
Okay.
2 represents both nitrogen and hydrogen?
Yes, the coefficient multiplies everything that comes after it,
And what about the subscript?
including the subscript.
So there is,
Let me ask the question again. How about that? Is the equation balanced? Who says yes? Okay, who says no? Okay, so it is balanced, right?
No, there's 2 nitrogens.
The coefficient, remember, multiplies everything that comes after it by that. So we have 2 n's and 2 times 3, 6 h's. Okay, the coefficient multiplies everything that comes after it in that formula. All right, so what would be a mole-to-mole factor for the H2 and N2? H2 and N2, what's the mole-to-mole ratio? 1, 2, or 3? All we're doing is taking the coefficient, right? So we have 3 moles of hydrogen for every 1 mole of, this is a 1, that's not the plus, for every 1 mole of N2, right? 3 moles of hydrogen for every 1 mole of N2. And then the relationship between the ammonia and the NH3 and the H2, right? So the NH3 here, we have 2 moles of NH3, and the H2, we have 3 moles of H2. 3 moles of H2 for 2 moles of NH3. 3 moles of H2 for 2 moles of NH3. We're reading the coefficient as a mole-to-mole ratio. That's all that this is. It may not seem like a big to-do about something, okay, but it's actually the most important part of this whole stoichiometry business, because it actually relates one thing to another thing in the equation. It's sort of like the hub of your stoichiometry wheel. Yeah.
I'm sorry, I guess I'm not understanding on the subscript 2.
Yes.
I understand that there's 3 moles of hydrogen.
Right.
What about this 3? Okay.
So all we're looking at is the coefficient, right? 3 moles
Oh, we're
of
still
H2.
on this side? Okay.
Yeah, 3 moles of H2 for 2 moles of the NH3.
So there'd be 1 mole of N2 to 2 moles of NH3.
Correct. 1 mole of N2 to 2 moles of NH3. Okay, if your equation isn't balanced, that ratio is going to be wrong. So it has to be balanced. It must be. If it's not, you have to balance it. Okay, so how are we going to use that information now? Right? That's the most important part of this. How are we going to use the mole-to-mole ratio to get from one thing to another thing in a chemical equation? So here we're asked how many moles of Fe2O3, which is iron 3 oxide, can form from 6.0 moles of O2. Okay, so let's start this slowly and work our way through this before we start running and jumping. So what are we given? What do we need to get to? Right? The same 2 questions we've always asked ourselves. And the third question, what are we going to use to get there?
What do we have?
you're given 6.0 moles of O2.
Okay, hang tight for a second. So the next thing, once we figure out what we're going to ask ourselves, right, we're posed with a chemical equation. What should you make sure of?
It's balanced.
That it's balanced. Okay. Is it balanced?
Yes.
Yes, it is. 4 FEs on the left, 4 FEs on the right, 6 O's on the left, 6 O's on the right. Okay, you need to be relatively proficient when it comes to balancing equations, right? You shouldn't have to be spending something like this. It shouldn't take you more than
2 seconds.
a minute to balance this. This is a relatively simple equation to balance. Okay, if you find yourself spending a lot of time on something like that, you have to practice a lot. Okay, so we're given 6 moles of O2. We need moles of Fe2O3. So we need a relationship between those two things, between the O2, this, and the Fe2O3. What is that relationship? Raise your hand. Yes.
3 moles of O2 over 2 moles of Fe2O3.
3 moles of O2 over 2 moles.
Moles of Fe2O3.
Okay, so all you did there was just read the coefficient from the balanced equation. Right, that's a conversion factor. We can flip it if we need to, and let's just write the other one just in case. So we have 2 moles of Fe2O3 for every 3 moles of O2. Right, that's the same thing we've been doing the last couple equations. So we use those two things, those two relationships, because they related the two things that were given, the O2, to the thing that we want, the Fe2O3. Right? That's the mole-to-mole, coefficient-to-coefficient ratio from the balanced equation. So then we can go ahead and set this up. We start with what's given, 6 moles of O2. Okay, and now we're going to use one of those two conversion factors. Which one am I going to use, the left one or the right one? Units are going to guide you, right? Which is why you don't just write the number, you write the entire thing out. Moles of what, right? So if you want to cancel out moles of O2, we want to put the moles of O2 on the bottom. So 3 moles of oxygen for every 2 moles of Fe2O3. Moles of O2 go away, right? So we can do a little math in our head. 3, that gives me 4.0 moles of Fe2O3. So I can calculate how much of the product, the iron 3 oxide,
Is that right?
I should get. Is my math wrong? I'm sorry.
You're right.
You're right.
That's a 4, not an H. Let's see here. So that's 4.0. Yeah, 6 times 2 is 12, divided by 3 is 4. So we can use the mole-to-mole ratio, in this case, to calculate how much of the product we should get if we know how much of the reactant we're starting with. Right, and that's the key piece of info we get from our balanced equation, that mole-to-mole ratio that connects one thing to any other thing in the equation. All right, let's take a look at another one. So it says how many moles of Fe are needed for the reaction of 12 moles of O2. Okay, so why don't you take a minute and do this one on your own. Set it up the same way. equation is already balanced. We just used it. Yeah.
And the exam will tell us if it's balanced or not.
You should always assume, should always check. You should never assume that it's balanced, all right? Unless it specifically says balanced, all right? Assume that it's not. So we're given moles of oxygen, 12 moles of O2, and we need moles of the iron, right? So here we are relating both of the reactants to each other, right? This thing to that thing. So we're going to use, right? We're not really concerned about the iron oxide because we aren't given any information about it, nor do we need to find anything about the product. We can just disregard it. If you start to think about it, then that's how you end up overthinking things, all right? What are you given? You're given the moles of O2. You need to find something about the iron, the other reactant. So we need a relationship between those two things, right? And that relationship is simply the coefficients of those two things expressed as a conversion factor. So we just simply put them over each other. 4 moles of iron for every 3 moles of O2, right? The 4 from the iron and the 3 from the O2. And then we'll just write the other one. 3 moles of O2 for every 4 moles of the Fe. All right, so let's see. Let's set this up. We have our 12.0 moles of O2. All right, I want to end up with moles of iron, so that means I'm going to use this one. Agreed? Yes, because the unit I want is on top. By default, the unit I want to cancel is going to be on the bottom. So 4 moles of Fe for every 3 moles of O2. Moles of O2 cancel. All right, and that's going to give me, do a little quick math. Hopefully it's right this time. 16 moles of Fe. So from the balanced equation, we get those mole-to-mole ratios that allow us to go from one thing to another thing in the equation, whether it's a reactant to a product, or in this case, we've seen a reactant to another reactant. Questions so far on mole-to-mole ratios? Okay, it really isn't ultra complicated as long as you have your balanced equation. Right? We're just pulling out the relationships and expressing them in a way that we've used ever since week 2 when we started looking at dimensional analysis and unit conversion.